This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Homework, or maybe homework reading, where I was asking, specifically, how can you get, what do you need in order to be able to get a flat power spectrum? And one of the things that I did ask you to just become familiar with was the concept of Fourier transform, and then the square of the Fourier transform gives you the power spectral density. So I believe a lot of you should have done this, or should be familiar with this. But anyway, if you're not, please, I won't go through it, but what I want you to do is actually be aware of what does power spectral density mean? How do I, if someone gave me a signal, how do I determine the power spectral density? And of course, if I had a noise process, how do I determine its power spectral density? And there, what I briefly touched upon was this concept of autocorrelation function and working out the Fourier transform of the autocorrelation function in order to be able to work out the power spectral density. Then what we talked about was what is, briefly, the power in a particular bandwidth, and what we started to talk about was this concept of the power is equal to KTB, right? Which is K was Boltzmann's constant, T is what? GF's temperature in Celsius. Okay, good. Temperature in Kelvin, and B is bandwidth. Fantastic. Okay. And what I did here was actually went through the process of being able to describe or calculate for you, if you had a particular bandwidth and a particular temperature, how do you work out the effective noise in that particular bandwidth? Okay, so we went through that. And then the other thing that we did was, if we had a specific resistance, what we did was to go through and calculate an equivalent voltage, RMS voltage, that we would expect to see from that particular resistance. Then the next thing that we did was we briefly touched on noise figure. We talked about an equivalent noise temperature. I think that's pretty self-evident, so I won't go back into details on that. We talked about noise figure, and essentially what we started to talk about was that noise figure, I've mixed up the slides a little bit, is essentially the change for a particular element was the change or the ratio of the SNR out to the SNR in. Okay, so if you've got a noise, a device like a power amplifier has a noise figure of n dB, say 10, what it means is the SNR in or the SNR out is 1/10 the SNR in, right? Now, one of the things that people constantly get wrong and constantly get confused about, and I just want to re-emphasize this before we move on, was the concept of what is the noise figure for some lossy element, some passive lossy element. Okay? So, for example, if I said to you, I've got an attenuator and it's got 4 dB loss, what is its noise figure? Perfect. Right? Just remember that off the top of your heads. You just be always like, I've got an attenuator or some kind of lossy element. It's got a loss of L dB. Its noise figure is L. Right? Also, what is its gain? Minus L. Perfect. All right, good. Fantastic. Now, the next thing that we started to talk about, and this is important, I'd like you to, we talked about it briefly, but one of the things that I want you to be aware of is how do you work out the noise or the equivalent noise figure for a cascade of elements, right? And this is absolutely critical when you're trying to develop or determine the performance of some kind of transceiver that you might be designing or producing, right? Now, what we've gone through, and you can actually derive, or essentially what you can actually see, is that the noise figure, the total noise figure, is the noise figure of the first element plus the noise figure of the second element divided by the gain of the first, plus the third element divided by the gain of the first and second elements. Right. Now, there were some important key takeaways here which you need to be familiar with. What are they? If you're designing a receiver chain, what does this formula tell you? What should you immediately, if you're designing a receiver, trying to design a highly sensitive receiver, what are some of the key takeaway points that this formula is indicating to you that you need to do?
First amplifier should have low noise.
Should have low noise and highest gain as possible, right? Because why is that? Yes, you're absolutely right. Why? Yes. Right, absolutely. Absolutely. So what it's actually saying to you is, if you're designing a receiver, in this particular case, one of the things that is absolutely, what you can actually see from this formula, especially as you draw it out, is that your first element contributes the most of a noise figure, and then the other elements in the cascade can contribute less, provided that these gains are large numbers, right? If the second element was if it had a low noise figure, but also had a lot of attenuation, as an example, then F2 might dominate, as an example, right? So ideally, if you're designing some kind of element, some kind of receiver structure, what you want is the highest lowest noise gain as early on as possible. And then what we did here, as an example, was we went through the process of understanding what kind of contribution to the overall noise figure that a little bit of coaxial cable might have to that system, right? And what we did there was, I went through and said, well, we had an antenna and we had a little bit of transmission line, it had a particular amount of loss, and then we had a gain, some kind of low noise amplifier. And we quickly realized that this little bit of transmission line had a significant contribution, or can have a significant contribution to the overall performance of that system. And the reason is not only because of the noise figure introduced by the loss, but also it causes amplification of the loss of the noise figure of the following on stage. Okay. So that gave us a little bit of insights on how we would do, or some system level insights into transceiver design. Now, what I'd like to move on to for this lecture was, we've gone through stability circles, we've gone through gain circles, and guess what? There's going to be noise circles, right? So therefore, noise circles essentially allows us to determine the effective noise that a particular amplifier would manifest given its input and output matching. Right? Now, usually what happens, and I guess I have to emphasize this, when you receive a transistor data sheet, usually what it does, it tells you these are the scattering parameters, this is Fmin, and the Fmin is achieved at a particular output impedance, output reflection coefficient, I should say. So what that allows you to do is, under certain circumstances, it allows you to trade off gain versus noise figure. Right? And as we saw, it's not always the case that the best noise figure, the lowest noise figure is the best, because there are circumstances where you want to trade off noise figure and gain, right? Because depending on how much noise the next stage has, as an example, if you if you might be able to tolerate a little bit noise from that particular transistor, right? But it significantly reduces the overall contribution to the noise figure of the next stage. Right? So what we've done is, and I won't derive it, but at least what you're able to do is you can actually see, or in POSA, or microwave engineering by POSA, you can actually see that the noise figure for a two-port amplifier is given by this relationship, where Fmin is the minimum noise figure for that particular element, in this particular case a transistor, and what we have is this other element called Rn, which is the normalized noise resistance of a two-port, the normalized source impedance, and then the optimal source admittance at the minimum noise figure. Now, if you go through all of this, what you can actually do is you can rewrite this equation as the overall noise figure in terms of the source reflection coefficient, the optimal source reflection coefficient, and that gives you the resulting noise figure. Now, as we've done in the past, what you're able to show is that you can now draw some noise circles, right? What is the minimum? Okay, so if we're going to do this, we actually work out the noise circles, and then you're given the center and of course the radius. What is going to be the minimum point? If you look at this, you can actually see, irrespective, because this is always a positive quantity, right? The absolute minimum in the noise figure is the minimum of the transistor itself, right? And that occurs at gamma S equals to gamma opt, right? So therefore, you're able to always draw that point in your Smith chart. Now, what we're showing here is if we're choosing some other value, or we're trying to determine some other noise figure values rather than the optimal noise figure value, what we're able to do is to draw a sequence of circles which represent these other noise figures. It's equivalent or analogous to what we did in gain, right? There's always this capability of getting the maximum transducer gain or the maximum available gain. You can only achieve that at one particular point, right? But there might be situations where you're saying, well, hey, I don't need to have the optimal. What happens if I'm a little bit off? Like I've added a little bit noise. What are the potential, impedances that give me that particular noise figure? Why would you want to do that? Can anyone give me examples or some insights on why I might want to why I might want to do that optimization? Okay, so suppose suppose you wanted a different gain. We've already talked about that. What other things? Maybe your maybe your transistor's not unconditionally stable, right? So therefore, you might want to choose a different set of characteristics that you've got a different gain and a different noise, but you achieve some other desirable properties for the system that you're developing. Maybe the voltage standing wave ratio is too high or something, right? And that's the reason why we do that. Now let's look at this particular example. And what we're going to do is go through the steps of working out the effective noise figure. So essentially what I've given you here is, hey, we've got some of the scattering noise parameters for a bipolar junction transistor, and for whatever reason, suppose we've referred to a data sheet or something, we've been provided with the scattering parameters, and we've also been given it's been given to us what the minimum noise is, noise figure, the impedance at which that occurs, and Rn. So the very first step that we would do is, of course, calculate the stability, right? And in this particular case, we've worked out that the system is unconditionally stable, right? What does that mean? We've gone through this hundreds of times, so I'm just trying to make sure I'm hearing feedback, right? What does unconditionally stable mean? For any input or output impedances on the Smith chart, the system's stable, right? So for any passive input or output load, we're okay. But what other thing does it tell us? If we were trying to work out the maximum transducer gain, what can we do? Okay. Remember when we were doing when we were working out gains of power amplifiers, in order to work out the gains of power amplifiers, one of the things that we did was we started off by doing some more simple analysis, which was, let's do this unilateral approximation and see what happens in terms of determining the gain of the overall system, right? And then working out what the optimal source and load impedance is in order to be able to achieve that maximum gain, right? Now, if we look at this particular problem, we see that S12 is non-zero. So we know that it's not unilateral, right? Now, we may be able to use the unilateral approximation, right? But then that means we've got to do a little bit of work in order to see, does that unilateral approximation actually hold? But we know something else here. We know that the system is unconditionally stable, and as a consequence of it being unconditionally stable, it means that we can do what? In terms of matching. It means that we can do a bilateral conjugate match, right? Remember when I was drawing the flowchart of all the things that you can do, what I was saying was, hey, if you can either do this unilateral approximation and work out, the optimal source and load impedance, or the source and load impedance at which you believe will give you the maximum gain. But but after you do that, you've also got to ensure that that unilateral approximation is a valid approximation. And usually, what we say is, what we do is we work out that U, which was the upper and lower bound on the error, and usually we said if it's a quarter of a dB or less, we're all, Bob's our uncle, everything's good. But we then went through the process of saying, well, what happens if it was not unconditionally stable? And then we also went through the process of saying, well, what happens if it's unconditionally stable? Can we do something better? And then at that particular point, we talked about bilateral conjugate matching. And in this particular case, if we're doing a bilateral conjugate match, we can actually work out what the optimal impedances are in terms of the source and load, which gives us those characteristics. And what we do here is we can actually work out what these values are, but also importantly, what we can do is also work out what our maximum transducer gain is for this particular amplifier, right? If we had complete freedom in order to be able to choose the input and the outputs, right? And input and output loads. And of course, remember, the reason why we're using bilateral conjugate matching is because it gives us the optimal value, but also it takes into account that, the output reflection coefficient depends on the input, and the optimal input reflection coefficient depends on the outputs, right? That's the price that we pay once we have S12 not being equal to 0. Anyway, if we go through that, we can actually work out what the optimal impedances are, and of course, we can actually work out K, and in this particular case, K is approximately equal to 1. It's, K is 1.012. If we substitute that into this formula, we've got K is equal to, magnitude of S21 on S12, and when we see that our maximum gain for this particular transistor is going to be, if we were using this transistor in order to make an amplifier, is 14.7 dB. That's the best that we can ever hope to achieve if we bias this particular transistor as the way that we've just described, and we had those particular scattering parameters. Now, what I've done next is then say, well, if we go through this process and we look at this bilateral conjugate match, we can also work out what our optimal impedance is going to be. And what I've done is just done a substitution. And remember that all the values, including noise figure, have to be in linear scale. Do not use dB. It's not appropriate when you're using any of these formulas, including Fourier's equation. And once you go through all this, what you find is that this particular amplifier, once you match, or this transistor, once you match it for, maximum gain, you get a whopping 17.66 dB of noise. Or, sorry, its noise figure is 17.66 dB. So its optimal value of noise figure was 2.5. If we were trying to get maximum gain, the absolute maximum gain, what we find is the noise figure is 17.6 dB. All right? Not ideal. Because what happens if we were using it as an LNA? Right? Even though it had, what was the gain? 14 dB of gain, but 17.6 dB of noise figure, terrible. Right? I wouldn't use it as an LNA. I might use it as a power amplifier, maybe, but I would never use it as an LNA. It would be completely inappropriate. Okay? So how do we now use this and what we've just seen here in order to start designing some low noise amplifiers? Right? Okay, now I apologise. I was writing my lectures this morning and then I got distracted and then I haven't put them online as yet. What I'll do is when I get back to the office I'll put them online. So my apologies for that. Anyway, so the aim here is we saw that going for optimal noise, going for maximum gain doesn't necessarily give us the best noise figure, and sometimes it can be a complete disaster, as we've shown in the previous example. So the aim here is what is a process that we can actually use in order to be able to design an amplifier which has reasonable gain, but also some desirable noise characteristics. Okay? And generally, what I've done for you is, Posers just puts it down. What I've done is I've actually split it up into steps for you so you can actually go through step by step, more a recipe-like approach in order to be able to work out what you need to do in order to work out what the, how do you achieve a particular noise figure for a particular gain. So the 5 general steps in the design of a low noise amplifier are as follows. 1, you're usually going to work out what your desired gain is, right? But of course, so maybe there's even a step A before that. And the step A before that is to actually work out your stability circles. Is the system stable? And which parts of the Smith chart is the system stable? So therefore you know which load impedances and source impedances don't cause you any issues. But then we follow step number 1. People are beginning to laugh. Am I doing something silly? Yes? No? All right. If I am, let me know. I mean, I'm pretty good at laughing at myself, so it's okay. So what we do is we know that we want to achieve some kind of gain. And in this particular case, what we do is we say, well, let's work out what the gain of this transducer is going to be. And usually what we try to do is, a lot of times we make the unilateral assumption. And if we do that, what it says is that the gain is essentially the gain of the source network, gain of the transistor, gain of the source, transistor, and then the output network of a load, right? Because you remember that remember in our lectures we had GT was equal to GS, and we had worked out formulas for GS multiplied by G of a transistor multiplied by G of a load. And essentially what I'm doing here is you work out, of course, if you're using the unilateral approximation, what is the gain of the transistor? What's the maximum gain of the transistor if we're using a unilateral approximation? S21, magnitude of S21 squared, right? That's the maximum gain. All right. So what we do here is, if we know what S21 squared is, and we've calculated that in dB, the only other degrees of freedom that we have available to us is to choose what's going to happen in terms of the gain of the source network and what's going to happen, what are we going to allocate to the gain of the load network. So for example, you know, if we had an example, and we'll go through this particular example in the next few slides, if we wanted to build an amplifier which had 16 dB gain, and the transistor gain, or S21 squared, was 14 dB, it means that we've got ability to choose GS and GL, the sum of GS plus GL, to be 2 dB. Right? As an example. And essentially that's what I'm saying in step number 1. You just assign how much do you want for your source, how much you want for your load, and usually what you do is you assign it in such a way that you get the noise, a requisite noise figure, and also some desirable voltage standing wave ratio characteristics. Now, the next thing that we do as part of this design is we plot the source constant gain circles and the constant noise figure circles. Right, so for example, if we were choosing 3.5 dB as noise figure, we go through the process. We know where gamma opt is. What we also do then is work out the 3.5 dB noise circle. We draw that on the Smith chart. We also draw the source gain, how do you call it, gain circle. Question, all right, it's a unilateral transistor. Why am I only telling you or suggesting to you in step number 2 to look at the source gain circle and not the load gain circle? Any reason? Okay, if I put this formula up again, can anyone tell me now?
Because the noise only
Depends on the source. Right. Okay. Good. All right. Okay, so step number 3. Step number 4, we choose the desired gamma S in order to achieve our desired noise figure. And then step number 5, what we do is we plot the load constant gain circle, and we just determine and choose the appropriate gamma L in order to complete the design. Okay, some excitement. Let's put this procedure or recipe into practice. Okay. Okay, now I can hide. The advantage of me not putting up the lecture notes is I can start doing this, and I can actually start getting some interaction from you guys. Okay. Suppose it was an exam question, all right? Or, even better, you were doing this because you wanted to build a real amplifier, all right? And you were told, hey, you've got this transistor which has these characteristics. These scattering, after you've biased it, it's got these characteristics. And what I want you to do is build for me a low noise amplifier which has a noise figure of 3.5 dB and a power gain of 16 dB. All right? What would you do? What is step number 1? We work out the stability, right? Okay. That's unfair because, I mean, we always say we work out the stability, right? So in this particular case, we know K is infinity, and we also know in this particular case S12 is equal to 0, right? So therefore, the unilateral assumption is valid, right? So therefore, we know that if S12 is 0, we always know that it's going to be a stable system. But anyway, so we know it's unconditionally stable. Good. What do we do next? All right. Let's work out what we expect the gain of this system to be, right? So we've made the unilateral assumption. So we haven't even made an assumption. We know that the system is unilateral because S12 is equal to 0. Now, if I gave you this, the S parameters in this matrix form, right? You all know which one's S11, which one's S12, S21, S22, right? Anyway, I've written it here. Just make sure that you know that, because on the test or an exam, I might not draw it on there. You should be able to know that off the top of your head, right? That's simple stuff. That's okay. So as we discussed just previously, we know if we're doing a unilateral amplifier design, we can separate the maximum transducer gain as the product of the gain of the source, gain of the transistor, gain of the load. Okay. All right. Now, we know... Why am I working out GS max? I've asked you... Okay, so suppose we know what G naught is, which is the gain of the transistor, right? And because we've biased it a particular way, S21 squared is something, and it's saying it's giving us 14 dB gain. Now, why am I working GS max and GL max? Other than, why am I working it out? What's the significance? Or what's the importance, I should say? Yes, exactly right. Right? If you, for example, if I had said to you, I want a power gain of 18 dB, well, the sum of these cannot exceed 18, so therefore you'd say to me, Stan, it's impossible. But the other thing that I'm also saying is, even though the number here is 16, which is going to be less than the 18.3 dB that you can actually get out of this particular transistor for any source and load impedance that you choose, when you're doing your design, you've got to make sure that when you're choosing your GS max and your GL, that your GS max is always less than 3 dB for this particular transistor, and your GL max is less than 1.3 dB. Right? That's the only choice that you've got, right? If you try to go, if you try to exceed this, you got nowhere to go. But also, what it says is it gives you an indication of where you can actually start reducing gain and start playing around with the gains in order to achieve your desired gain, but also then try to optimize then your noise figure for your overall amplifier, right? Because we're trying to build a low noise amplifier which has, 3.5 dB of gain, noise figure. Okay. All right. So we've worked out GT with GT max, and we know what GS max, G naught, and GL is. Okay, excellent. Now, so we know what the overall gain, maximum gain is going to be, right? Now, the next thing we've got to do is allocate gain. How much do we allocate to the source and how much we allocate to the load, right? And remember, in terms of noise figure, it's actually only the source network which contributes to the overall noise figure. The load network doesn't do anything as far as the noise figure is concerned, right? So therefore, it's just now, if you tell me why did I choose these numbers, well, part of it's because it was an example somewhere, and B, they chose it for no particular reason other than to make the mathematics easy, right? But generally what you would do as part of this process is you would try to choose your GS max and GS and GL so that it was able to meet your design criteria. All right, and for argument's sake, let's say we were told these are the values that we're going to choose, and we chose them such that, 14 plus 1.2 plus 0.78 gives us the desired 16 dB of gain. Now, the next thing that we've got to do is we've got to plot our gain circles. We've got to do two things. We've got to plot our gain circles, and we've also got to plot our noise figure circles, right? So let's do that. So what we said is we want to plot, in this particular case, we're saying that the source impedance that we're going to choose is 1.22 dB. And we work out, remember, the gain circles. And remember, when we're plotting the gain circles for any of the gain circles, we've got to define this concept of GS on this little GS, which is the actual gain divided by GS max. And this is the other reason why we needed to calculate it. And we know when we go through this process that the centre, and we had derived this in the past, of the gain circle is at this location, and the radius of this gain circle is given by this value. So if you go through this, what you're able to show is that GS is 0.67, and you can work out that the centre of the gain circle is at 0.56 angle 155, and the RGS is 0.35. I haven't worked out CGL. I mean, I'll leave it to you to work out at some other stage. All right? Now, I'm going to work out this value of n, which I then use in order to work out the centre for my noise figure circle, and also the radius of my noise figure circle. All I've done here is just use the formulae that I, had derived or actually copied out of POSA. And had presented to you, at the start of this lecture. All right. So, how would we draw this, and what would we do? Okay. So the first thing that we would do is let's work out our location of our gain circle. Now, what have I done here? You're probably going to see, Stan, this looks different. What have you done here? This isn't the Smith chart that you usually put up. Well, what I did was I was a bit ambitious last night. I was getting a bit bored, so I decided to look up Smith charts, which not only had Z, but they also had admittance plotted over each other. So what you might not be able to see this, but once I put it online, and you'll see there's red lines, which you can actually see. Let me try to focus in a little bit. But you can also see the blue lines, which are your admittance lines, right? So this is a Smith chart that's got both your impedance and impedance and admittance lines relative to the one that I've been usually using, which is just only impedance. Anyway, don't say that I don't try to make the lectures exciting. All right, now, first thing. All right, we're going to work out the centre for our gain circle. All right, so what do we do? How do we calculate this? Just, we're going to work out gain circles and stability circles, and they're going to be on your test. So you might as well contribute to this and tell me what we're going to do, so therefore you can get ready for your test in the next, 14 days or something. All right, how do we work out we've worked out the centre of the gain source circle. How do we plot it? What do we need to do? And we said that the value was 0.56 angle 155 RGS, or the radius was 0.35. What do we do?
Match the radius at the bottom.
Okay. Yeah. So what I did, yes, is the first thing I did was just find 135 degrees here, right, and just draw a straight line, right. So therefore I know we're 135 degrees, and it's a positive 155 degrees. So I apologise. Find 155, just draw a straight line through it. Then, as your colleague has just pointed out, we've got to then work out the value of CGS. And what do I do there? You correctly said that?
The bottom line.
Yeah, I do. Yes, and I apologise. It's a little bit I don't know if if it appears better for you guys, but I'm also a bit blind. So anyway, what we do is we try to find 0.56 on the reflection coefficient down here. So we find 0.5, 0.56, and remember, I'm a terrible drawer, so I apologise. So essentially, what we do is, we find where that line intersects, where that point intersects the line, and we draw it. So we draw CGS. Fantastic. That's the centre to our circle, a gain stability circle for 1.22 dB. What do we do next? Sorry? Oh, no. We've drawn the centre. Okay, now do the radius for this gain stability circle. What do I do in order to work out the radius of the gain stability circle? Okay, sorry? Okay, the radius is 0.35. What do I do? Yeah. All right, 0.35, let's do this. All right, 0.35. What do I do next? But where? In here?
At the center, we just...
No, I'm trying to make sure that you all know, right? Yes, I know what I'm supposed to do, but I'm trying to be dumb so that I can get you guys to participate. Right, so what we do is we go here and we draw the circle around this point. Fantastic. Bob's your uncle. Good. All right, now we've got to also draw the noise figure circle. Okay. We know that the centre of the noise figure is at 0.37, 180 degrees, and of radius 0.39. Okay, what do we do? Let me put it here. All right, so that's the centre, that's the radius. Okay. So all I'll do is, of course, so I won't bore you all, we know that this is the 180 degree line. I work out 0.37, look it up here, draw that point, right, 0.37. I haven't done it properly here now, but 0.37, find the point, draw the line, draw the radius. All right. Okay, so now what we can see here is I've got my noise figure circle, and I've also got my stability circle. Now, I've also drawn one extra circle in there, right? What's that circle and what's its significance? I didn't put it in the steps, but I probably should have, but you should recognise that circle anyway. Sorry? Yeah. I've also drawn the 1 plus JB circle in there. And the reason why I've done that is it actually helps me in order to determine, what I need to do in order to get the appropriate reflection coefficient. But the reason why I chose this particular Smith chart, which has both impedance and admittance, is that it allows me to do some tricks that I can't do on I don't have to do the reflection method that I usually do. So the first thing is I want to work out a point which allows me to get 1.22 dB gain and a noise figure of less than 3.5 dB. Right? How would I identify that point? So tell me, where is 1.22 dB? Sorry? So we know that this circle is 1.22 dB, and anything inside this circle has a noise figure of less than 3.5 dB. Right? So essentially what I'm saying, for everyone's benefit, is anywhere here, if I wanted a gain of 1.22 dB and a noise figure of less than 3.5 dB, anything on that line, on that, I shouldn't call it a semicircle, on that arc will give me those characteristics, right? Because it's inside the 3.5 dB noise figure circle and it's on the 1.22 dB gain circle, Right, now, any of those points are valid. So if you were in a test or whatever, and you said to me, oh, I'm going to choose this point or that point or anywhere here, yes, fine, you got the answer right. But what I would recommend is, if you're doing your design, is also that you want the minimum voltage standing wave ratio, right? So therefore, what you would try to do is find also the point with the smallest radius, right? Because if this was your overall impedance, what you want is, you want to find the VSWR circle which has the smallest radius, because that gives you the lowest voltage standing wave ratio at your inputs. Okay, so you chose, let's for argument's sake, say we chose this point. All right, question. How do we build the input network that gives us those characteristics? Okay, I'll give you a hint. So we've got a source generator, and this source generator, and I should finish because everyone complains, I've gotten complaints that I keep you too long. I get too excited with the questions and keep you too long so you don't get to your next classes. But if you had 50 ohms, right, essentially what we're saying is you can add a shunt and a series elements, right, in this particular case, because we're inside the 1 plus JB circle, that allows us to then match that, right? So essentially all I'm saying is we're starting here. So what I'm going to do is I can add a shunt capacitance and then a series inductance so that I can get the requisite gamma S. All right, and once I do that, I can work out what the C and the L is, so that I get 3.5 dB noise figure and 1.22 gain on my source network. And then of course you would do your gamma L circles and work out what the gain is there. Anyway, I want you to think about this. What I'll do is I'll put the slides on LMS, and then what we can do is we'll have a little bit of a discussion next lecture tomorrow, and we'll take it from there. And then there's a couple more things on how we do you know, amplifier, low noise amplifier design before we move on to oscillator design. All right. Here I've got a source and admittance chart which is slightly different. If that's what's confusing you, what you would do, just in case you're getting confused, what you would do is you would move here, you'd move across. If you had a Z, it'll reflect there, and then you move across this way, and the angles are exactly the same. All right? Anyway. All right, cool. See you tomorrow. All right. No, it's it finishes. We're supposed to finish early, aren't we? Not the. I mean.
Okay, it's just a question. I mean, I'm cool with that.
Everyone tells me that I finish too late, and everyone complains. So I don't know what time it's supposed to finish.
I don't know. I think it was 2:15. Oh, well, 3:15. But
Anyway. Everyone's been complaining. I've received complaints that I finish too late and people can't get to the next lecture. So I thought I'd finish at roughly 3:10.
Cool, fair enough. Okay.
Because your next lecture's supposed to start at 3:15, right?
Yeah. Well.
Yeah, if you had another lecture, it starts at 3:15.
Probably.
Yeah.
Question about the speaker.
Yes.
Last one.
Yep. It's not only this one. Yep.
So I think maybe the procedure should be like we want to achieve like the gain and the noise by by doing this point, right?
Which is
this one, and then we want to do the mesh.
No, we're not trying to do the match. We're trying to get to that point because the amplifier is already 50 ohms. The source generator is 50 ohms. We want it to look like that point.
Why that's already 50?
Because it's a source generator. So suppose you got a source generator which was 50 ohms.
Oh, you assume it's already 50.
It's 50, and what I wanted to do is, I don't want it to look like 50, I want it to look like this, so that I can achieve
So
my noise.
we should this shunt
Yeah, and then
and go back with
Otherwise, if we want to do the match, we should go this way.
yeah, exactly. It's the opposite. Yes.
So, can you why is it opposite?
Because I don't want. What I want is I'm starting at 50 ohms. Usually, what we try to do is match to 50 ohms. But here, what I'm saying is, I don't want to match. What I want to do is work out the impedance that gives us the desired noise figure. Right. So I'm doing the opposite now. So I'm starting here, and I want to get to here. Rather than usually what I usually do is, we've got this impedance. How do I get there? Here I'm saying I'm here because hey, it's a 50 ohms. How do I get there?
So that's why we first have the shunt and
Yeah.
and then have the
To go up there.
usually these components should be opposite. I mean,
We're in the 1 plus j. Yeah.
so this is the source.
No. The source. This is the source, and I'm trying to look into it. And what I want is I want a desired.
Okay. Yeah. Then why this impedance in front of the capacitance here?
Because
I think we should first add the shunt capacitance.
yeah. Oh, no. But shunt capacitance. If you go shunt capacitance, all right. It doesn't matter. I'm using a different Smith chart. All right. You add the shunt capacitance, right?
So I think this is L, this is C.
Yes.
And we firstly add a C.
Right.
Then why the C is here, is not here?
What do you mean? No. But I'm starting from here. I want it to look like this, right? I'm starting here. I'm adding shunt, right? And then I'm adding this because I want it to end up to this point.
Yeah.
I'm doing the opposite. I'm not trying to get to 50 ohms. I'm trying to get to. Anyway, I'll put it up. Have a think, and then what we can do is go through it again tomorrow.
also choose the TIGO 1.22 and 0.78 is arbitrary.
It's sort of it's less, and that's what they chose in the example. That's why I did it. Yeah, you're going to choose it. You choose it. What if you look? Usually, what you would do is you would look at it here, and you'd say, all right, you draw some gain circles, and then what you would say is, how would I design it to get 3.5? You might actually choose it a little bit more, a little bit less. You know, in this particular case, it was arbitrary. Arbitrary in the sense that that's what they chose in the example, and it was just so that it gives me 16 dB. All right.
Okay, so I think the main reason is because we're looking at the reflect coefficients into the source.
Yes.
That's why I start. Yeah. That makes sense.
All right. Cool. All right. Excellent.
By the way, so we have we'll have a problems. I will have a questions in the mid semester test about the amplifier design.
Yes.
Will it include the noise?
No.
So it's just maybe 2 weeks.
Yeah. Is it recording? It's still recording. I want to do two things, right? I want to teach you some stuff, but I don't want to make it too difficult so then you guys don't get good marks. So it has to be, but I have to make this difficult so you learn, and then but do some of the stuff that you can also get a good marks, right? So it's a delicate balance.
I just want to make sure I did the good
Yeah.
for that.
Yeah, and what I'll do is I'll write it up on the. I'll put some not slides. I'll put up some notes on the elements.
how to do that?
Okay, send me your CV. And CV, I want your transcript, right? Okay, okay. Because what we do, okay, so there's a reason why I'm asking for that. If you've got, depending on your marks, you get a scholarship.
Yeah.
Right, and that's the important thing, because otherwise, how do you pay for it? All right. So, and that's so if you've got a sufficiently good grades, that's all you do, and then when we take it from there, kind of thing. So what's your average?
Oh, because I have